Hi, I'm Seb. I'm here virtually to present an OCaml project called SmartPy, which is a Python library and a meta-programming framework designed to implement distributed applications on the Tezos blockchain. It's quite a polyglot project that also uses Python and JavaScript extensively. So, who am I? So, hello, this is me. I'm a software engineer at TQ Tezos, a company whose role is to improve the Tezos ecosystem in general. I myself work on the core Tezos codebase. I also develop and help people develop smart contracts on top of Tezos. I also help our partners getting up to speed and build things on Tezos. I also contribute to the standardization efforts around smart contracts to improve interoperability. And I contribute to tooling development, and that includes SmartPy, today's topic. I'm not the main developer at SmartPy. Currently the team is 4 or less people. The project started and is led by François Morel of Lexify Frame. Roland also joined, recovering Haskell, who's working deeply in the compiler, decompiler, and has done many more things. Rodrigo joined more recently, first on infrastructure and then also on the web UI. And finally me, I've been doing a bit of everything over the last couple of years, more on the testing side, the testing framework that the users use, and our testing and CI setup, also on the implementation of cryptographic and blockchain primitives of the language. So let's define a few things before we lose all the audience. So Tezos is a cryptocurrency that is usually pretty well known in the OCaml world because there have been a few talks here and there, and we have been hiring OCaml and formal methods people for a while. A cryptocurrency, in one sentence, is a distributed system where entities that do not trust each other agree on a common history, usually using financial incentives and very clever cryptography. What's particular about Tezos is that it's based on a proof-of-stake consensus algorithm, so we use baking instead of mining. Tezos was actually the first large-scale proof-of-stake to launch. Proof-of-stake means that block producers are selected using their balance in the cryptocurrency, not the hashing power, as in Bitcoin. It also means that not like Bitcoin or Ethereum, it's actually energy efficient. Another particularity of Tezos is the on-chain governance. It's a self-amending protocol. Tezos can upgrade itself, and stakers vote on upgrades to the core protocol. So we often say that Tezos can steal other new good ideas from other projects without centralized hard forks, because we can upgrade. Then Tezos, like Ethereum, is based on smart contracts. We don't just have transfers of money between owners and private keys. We have accounts that are programmable. They can execute pieces of code that are called with parameters. Some examples of programmable accounts can be spending limit contract, which prevents somebody from spending more than 1,000 Tez over a rolling day, or a multi-sig contract, a contract that requires more than one person to sign to agree to spend money or to do an operation. And of course, the other particularity is the OCaml implementation. The main implementation of the Node client and baking software is written in OCaml, and the protocol itself, the thing that is being voted on by the stakers, it's a hash of a tarball of OCaml files. So OCaml is really central. Those files define a big functor that is used to decide what are valid blocks. So the contracts mentioned above are actually pieces of Michelson. Michelson is the VM, or the scripting language of Tezos. It is the language that the programs that the whole network of validators has to run to reproduce the transactions, to everybody understand each other. It has a stack-based and functional core. It's a stack language. It has clear semantics and typing rules. They are defined inside the protocol with a gigantic GADT. It can even keep track of all the types on the stack. And this is by far not the only typing hack in the code base or on the ecosystem. There is a strong emphasis on enabling formal methods and on being a proper compilation target, because actually writing smart contracts is very hard. Bugs are very expensive. You don't want your money to be locked or stolen from an account. And at the same time, VM languages like Michelson are very low level. Nobody wants to handle the stack. Very few people actually write it. There is an Emacs mode, but not very successful. This has led to the proliferation of many high-level languages that compile to Michelson. There's been Liquidity, LIGO, SCAML, Lawrence, Juvix, and many other popular ones. SmartPy is likely the most popular. And actually, as I said, it's a library designed to do meta-programming of smart contracts. It's not a language itself. So SmartPy allows you to generate Michelson and test those contracts. It provides all the tooling you may want. There is an IDE and command line tools. You can run simulation of contract interactions. You can also deploy and interact with the contracts on a test network from the WebIDE. It is a big mix of OCaml, Python, and JavaScript. OCaml being most of the logic, Python being the user-facing meta language, and JavaScript being the glue between everything and also part of the user interface. So, why Python and why Python at OCaml 2020? Well, it is one of the most popular languages in the world. It has an intuitive syntax for most people. It has pretty good metaprogramming capabilities. So the AST is programmable. It has decorations that are programmable. You can see that success in the machine learning ecosystem with like Torch and stuff like this. And moreover, people believe they already know Python. So it's also like a Tezos gateway drug. Users usually get started and hooked even if they don't realize that the really hard part is actually designing secure distributed applications. The meta language doesn't matter that much. So what happens in the implementation? SmartPy programs generate SmartML expressions, and SmartML is an imperative type-inferred intermediate representation. It's an ML-ish language. SmartML is implemented as an OCaml library. Itself, it can compile to native using for the tests or for command line tools, or to JavaScript, which is what runs inside the WebIDE or in the end user command line application. The library provides type inference, other program analysis, like code transformations and optimizations. It also implements the interpreter and the interpreter of the test scenarios. SmartML is technically more than a smart contract language, since it also does the client and off-chain side of things for testing. Then, of course, there is a compiler to Michelson and quite a bunch of Michelson to Michelson optimization. And for now, work in progress, there is a decompiler to generate Python from Michelson to be able to study existing projects. So let's look at a minimal example of a smart contract. Sorry for putting Python code in a OCaml 2020 slide. It's a pretty dumb contract that just stores a string value which can be updated only by one account defined only once at initialization time. So on the first line we see that SmartPy is a library. It's imported like any other library. There is no magic there. Then we see that we define a class called Hello World that inherits from the concept of contract, and it has an init method that is the initialization of the contract, and it corresponds to the initial state of the contract that is actually posted on the blockchain when we create the real contract, the real Michelson contract. One of the parameters of that function is the administrator, the address of the account that will be allowed to modify the storage, and the other one is the string, the mem field. So then there is an entry point. It is a function or a method that anyone it can call. So if you need any form of access control, of course you need to program it yourself. That's one of the things that make blockchain so nice and so dangerous. So here we do the check that the thing called sender, the sender of the operation, is the admin that we initialize the contract with, and if not, we just fail the transaction. We see the little SmartPy specific syntactic sugar. So the keyword if is already taken by Python's if, and it is useful for metaprogramming. You can generate different things depending on conditions. So here we use sp.if, which is a function that takes a block of code to generate it, and there is a little bit of syntactic sugar there to make it nicer. You can also do without it. Then line 13, we see how we create test scenarios. So this is also essentially metaprogramming, functions that generate SmartML scenarios. They can run in the SmartML interpreter or in a sandbox blockchain or even in a public test network. Line 16, we see how we create a cryptographic key pair for testing. It's a real deterministic key pair from the seed that we see there, Alice. That can sign, but it can sign messages and everything, and it works in the interpreter just as in the real world. So we are fully interoperable. So then we call a few times the contract, and we verify a condition about the state of the contract at the end. So let's look at a little demo to see how it looks for the end users in the WebIDE. So we see the contract that I just showed with the test in the WebIDE with syntax highlighting and everything. The user can compile and run the program. We see the initial state. We see the test scenario results. So successful and expected unsuccessful entry points. And we see the nice OCaml 2020. We see also that we can deploy the Michelson contract, means that we can go and see it. We can see the size is of the contract, which are important because you pay for the size of a contract you put on chain. You can see the heavily commented Michelson code. It's also good for teaching people how Michelson works. We can then deploy the contract in another page on the main network, or most likely on a test network. You can import many kinds of private keys, and you can interact with the contract. There's also a block explorer, like a contract explorer. You can add operations to a contract already existing by creating them from the web UI. There is also more like a wallet functionality. You can import your keys and manage them and talk to various contracts. There's also a Michelson itself editor. So for now, for studying Michelson, and soon for decompiling Michelson. But already it's useful to see the typing live in the code as comments. And then there is an extensive help set of pages. The reference manual, this is very complete. And at the very end of it, we see the other aspect, which is the command line interface to SmartPy that you can install and that we are going to discuss a bit later. So let's go through what happens at the beginning of the demo we saw just before. The Python code is executed by the Brydon interpreter, which is an implementation of Python in JavaScript. Then the only thing the code does is actually constructs serialized SmartML programs. That's everything that the Python does. Then the contract enters the JS of OCaml world. The SmartML library does the type inference, the type checking. It runs the scenario in the interpreter, reports the errors as it finds them, and it does the compilation to Michelson and all the other tabs that we have seen. And it gives the results back to the UI that itself constructs an HTML write pane that we saw in the demo. So, as we saw also in the demo, there is a command line interface to SmartPy. The point of it is to be extremely portable so that it uses Node.js and NPM, and that way it allows anyone using Emacs, Vim, or any editor to edit SmartPy scripts and test them and compile them. So how do we make another portable OCaml command line application with JavaScript? So let's look inside this thing. It's a bit crazy, but it works. So SmartPy.sh is a bash script. It knows how to install the SmartPy-CLI dependencies, the Python and JavaScript files, and the NPM dependencies. The JavaScript is the output of JS of OCaml, plus some hacks on top of it. So SmartPy.sh then calls the OCaml application when it's installed, and it's a command liner application. The JavaScript main is the concatenation of a prelude.js that loads NPM packages and the result of JS of OCaml compilation. Though overall it makes something that it's a bit slow, especially starting it up, but it does the job and people seem happy enough. Not that we need to call anyway the Python interpreter, so it's not a pure OCaml super fast executable. So let's see how this thing is made with a beautiful Dune rule that uses cat and sed to be the linker of the output of JS of OCaml. Well, the call to sed will be removed once we integrate the next version of JS of OCaml. It will be cleaner. So let's look at what that prelude.js looks like. It's about 100 lines of requiring NPM packages and then doing that weird async hack to make sure that those libraries are initialized when the JS of OCaml process takes over. There may be cleaner ways of doing this. I mean, using a library that works both in the browser and in Node. But note that cryptographic library is actually a bunch of C code compiled to JS. And this is how it's brought to the OCaml side. So we are happy users of the Gen.js API project. We use an interface file with attributes that make up the JS of OCaml bindings. Here we have the bindings to the verify signature and sign from Libsodium. It's all very clean and very nice to use. We also have bindings to base58 encodings for a few hash functions like break2b and sha256. We can see that we did not bother and we use the js.global instead of properly passing around the sodium object. It just works. We also had to re-implement a compliant version of Michelson's serialization primitives, so pack and unpack, because they are useful, for instance, for signing things and verifying signatures. And most Tezos libraries are not yet usable with JS of OCaml, but it's getting there. There is work being done. So this is how it looks Of course, it should be on the slower side, but it's not important in our case. If it fits in a blockchain, it's small data. Also, a few words about error messages and location. So it's a known hard problem in the OCaml world, multiplied by a lot in our case. So we need to report errors from the Python interpreter, which is actually the easiest because it's the surface. There's also the SmartML type inference and type checking. It gets trickier because of the metaprogramming, but it works still pretty well because thanks to Python's programmability of the metaprogramming. There's also the interpreter that can report errors. That's still SmartML, but we have two locations now, the line number with the test that failed and the line number with the place in the contract where the test failed. And then there's the compiler. We usually just display there are errors in the Michelson and we don't interrupt the user. We show the errors in the Michelson and we try to get rid of those errors in improving SmartML type checking because we want them to be caught as early as possible. But that's work in progress. And then there are like the worst ones, the Tezos type checker and contract origination errors. We want to avoid those at all costs. So if we get one of those, we consider that it's a bug in the compiler, but can still happen. There are other challenges with a Tower of Babel of languages. Python and JavaScript are easy as languages, but we need to actually know a lot about the language implementations, like the Brydon versus regular Python interpreters that are like not exactly the same. We need to understand when we run JavaScript in the browser in Node.js and what JS of OCaml does with it. So for that, we can do proper abstractions using the module system. For instance, the real Tezos client test interpreter, the one that is not yet in the WebIDE, it's used to run the sandbox test and in the command line, and it's there in the command line app. So it's functorized over the concept of Tezos client. It works in native and Node.js, and it's not yet actually implemented in the browser, but it will be. Also, we have observed a slight culture clash between OCaml styles and Haskell and traditional ML. It's hard to impose rules in that kind of project. There's already a bunch of code. How do people homogenize when the team is understaffed? So for example, I'm in the Gen Street style camp with labels everywhere and long names and so on, but how do I impose it to everybody? One nice success is convincing people to switch to OCaml format. We have a 16-line .ocaml format config file, which in fact is good. It means that even if I don't care about the style, I can convince people to switch to OCaml format thanks to all those options. Also, as I said, we need to deal with the slowness of JavaScript. It's noticeable, especially at the startup of the application, but usually users seem pretty okay with some delay, especially since the write pane has a lot of value for users. Let me talk also about something called FA2. Without much detail, it's part of a standardization effort around a common multiple asset contract interface. One of the reference implementations is in SmartPy, and it's a good occasion to abuse the metaprogramming features. So it's at the address there, but it's also available in the SmartPy IDE as a template. So it really uses metaprogramming. There are like 12 Boolean configuration switches that drive the code generation. There are also, but those are not completely independent. It's not like 2 to the power of 12, but still, they allow many contract variants for many use cases that are meaningful and that are not worth discussing here. But they also allow to do heavy benchmarking to try various implementation strategies. For example, we ruled out an optimization that people think is often useful, and it turns out it's actually negligible for a bigger contract. The blog post about the benchmarks should be out by the time this airs. By the way, not really SmartPy related, but if you like metaprogramming with big build system hacks, there's also a lot of OCaml code generation done from the Michelson output, and it's used to build a mini wallet benchmarks command line application in real OCaml this time. So of course, when the contract changes, we get type errors in OCaml code, which is what we all live for. So for now, we are quite successful. SmartPy has quite some good popularity within the Tezos ecosystem. The Telegram channel, Twitter accounts are very active. There are like online courses and actual applications being built with SmartPy. Other tools in the ecosystem also like directly support SmartPy. But of course, there's always a ton of things to do. Among them, we want to work on like making sandbox testing more available to the end users. It is available in the command line application, but we haven't had much feedback so far. It's not that easy to get started with it, and many users are allergic to the Docker desktop dependency. So we are also working on the web version of it, which is talking to a node from the WebIDE. We are also working on the Michelson decompilation so that users can study and integrate contracts that they found in a while. We want to also integrate other analysis like doing abstract interpretation to follow data ownership, or work some form of gas usage prediction. And aside from Michelson, we want to add other generation targets, like ways of parsing or interacting with a contract of chain, or adding more formal targets like YML or Coq. So this is the end. Thank you for listening, and happy to answer any questions.